wondered why you see a rainbow effect in a puddle with oil? Well, today's your lucky day, because I'm going to explain that to you, and maybe perhaps you might even learn something today on physics. Now, to understand why there's a rainbow effect in those puddles, we need to understand 4 wave tendencies. The first of which being reflection, then refraction, then diffraction, and then interference patterns. First off, we have reflection.
Reflection is something we see every day and is ultimately the reason we can see anything at all. When light hits an object, it reflects at the same angle it came in at. When an object is a certain color, for example red, the white light, which is light containing all the colors together, will hit that red object. The object will absorb all of the colors except for the red, and the red light will be reflected back out.
The second wave tendency is refraction.
Everything in life has a density, yes, even air. Though density is usually used in other applications, it also carries weight in an optics point of view. Waves travel at one speed in every medium, meaning light travels one speed in air and another in water. As a light beam hits the surface of the oil film, some of the light will actually go through the oil, but at a different angle than it came in at. This is known as refraction.
The third wave tendency we're going to learn about is diffraction.
Waves have the potential to bend around corners. That's why you can hear someone talk in the other room when the door is open. The smaller the gap, the more the wave will have to bend to get through. With a large gap, most of the wave can get through no problem, only needing the edges to bend in a bit. This is the reason why we can hear around corners, but not see around them. Light has such a small wavelength, and doesn't need to bend very much to get through, while sound, on the other hand, has a very large wavelength, and will need to bend to get through that gap, but that also means it covers a larger area after the gap.
The fourth and final wave tendency I'm going to teach you about today is interference patterns.
Waves for sound and light are no different than waves in water at the beach. They have a crest and a trough, and these play into diffraction. When two waves come into contact with each other, they create either a supercrest, a supertrough, or a node. As the two light sources head towards a screen, or a wall, or out of a puddle, it will leave a specific pattern. Red light, which has the largest wavelength of all visible light, will have a larger distance in between its spots than blue light. As you can see here, each frequency has its own spot in the pattern, and in between each spot, there's a blur due to the colors mixing.
So now that we've learned about reflection, refraction, diffraction, and interference patterns, we can bring it all together and explain interference in a thin film.
The initial beam of light comes in, some reflects off the oil while some refracts through it. That refracted light in the oil then reflects off the water underneath it. The light that reflected off the water then comes up and refracts out of the oil back into the air. An interference pattern is then viewed from the light being reflected off the oil and the light being refracted out of the oil. The light that came in was white light, meaning it had all the colors in it, so the interference pattern viewed is just the spectrum of that white light. Now you have enough information to understand interference in thin film.